Okay, now we are going to talk about another really fun topic, which is buoyancy. Right? How does this extremely massive metal steel ship float? Or how does this hot air balloon float, right? If you think about a free body diagram for this hot air balloon, if it's floating, it's staying at a constant height, its acceleration is zero, the net force on that balloon must be zero, but there is definitely a force of gravity pushing down on that balloon. So what is the force up? What is the force keeping this balloon afloat? We're going to call that the buoyant force, and we're going to be able to derive the magnitude of that force using something called Archimedes' principle. Okay, so to start off, let's play around with this simulation. This is another really nice PhET simulation. And feel free to play with this on your own. You'll have to download Flash, but it's a very useful simulation to try to understand buoyancy. And first, let's try to answer a question. So I have this brick right here, the 5 kilogram brick. I can put it on this scale, which is outside of the water, and read in newtons how much, what is the force of gravity acting on that brick, or what is the force of the brick on that scale, would be a more accurate way of saying that. And then I could put the brick on this scale, which is submerged underwater, and see what is the scale going to read, what is the force of the brick on the scale. Okay, and so the question is the scale outside the water going to read a larger number, the scale inside the water going to read a larger number, or will they both read the same number? Okay, so take a minute and think about this. Pause the video if you need to. I'm also going to just do this for you. Let's see, let's get the actual simulation up here. Okay, so I already put it on the scale there. So here's the brick. I can take the brick and put it on the scale outside of the water. It reads 49 newtons. Okay, that makes sense. The weight of this brick is m times g, so 5 kilograms times 9.8 meters per second squared, giving me 49 newtons. Okay, when I put the brick in the water and it submerges and lifts on that scale is reading only 24.5 newtons. So it's 24.5 newtons inside the water and 49 newtons outside of the water. Okay, so why is the scale reading something less when this brick is underwater, right? Does the brick weigh less underwater? What is happening here? So let's try to understand that. So, okay, the answer to this was the scale outside in the air read a larger number. Okay, so let's think about this a little bit more. The brick in the vacuum, or outside, is reading 49 newtons. That's how much it weighs. The brick under the water, the scale is reading 24.5 newtons. So let's try to understand this better by drawing a free body diagram. For the brick outside the water, there's a force of gravity pulling down on the brick, right? But there's also a normal force, or the force of the scale on the brick, right, which is keeping that brick from falling through the scale. And these two forces have the same magnitude and are canceling each other, so there is no net force acting on that brick. It is not accelerating. Now let's do the same for the brick under the water. Okay, when we draw the brick under the water, the force of gravity does not change. Right? The force of gravity only depends on the mass of the brick and the mass of the earth. Right? And those haven't changed, so the force of gravity on this brick is not changing. But we can see that the force of the scale on the brick is now smaller. That's this little orange line. Why is that? Well, now there's another force involved. There is a buoyant force. Right? The fact that this brick is submerged underwater means there is a buoyant force upwards on the brick. And so the force of the scale on the brick doesn't have to be as big anymore. It doesn't have to support the full weight of the brick anymore, because the buoyant force is also helping to support this brick. And therefore, the scale is just reading a smaller number, right? It's not accurately telling you the mass of this brick or the weight of this brick anymore, right? It's telling you just how much force is the scale pushing on the brick with. Okay, and you can actually play with these numbers a little bit. Again, the 49 newton is the weight. So over here, the normal force must be 49 newtons. But on this side, if the scale is reading only 24.5 newtons, that tells me the buoyant force on the brick must be 24.5, such that the net force in the plus y direction is equal to the net force in the minus y direction. Okay. So just to reiterate a little bit, the scale displays the force of the brick on the scale, right, which is equal to the magnitude of the force of the scale on the brick. And underwater, this force is smaller because the scale doesn't have to support the full weight of the brick. The buoyant force is also contributing to holding this brick up. Okay, so the weight of the brick hasn't changed, but the apparent weight has decreased. Right? So when you put this on a scale, it seems to be way less. If you were to try to hold this brick up underwater, it would be pretty easy to hold. Okay, so now we want to try to quantify this effect, the buoyant force. And we're going to do that with something called Archimedes' principle. And just a quick summary, an object immersed in water seems to weigh less than when it is in air. We can call this apparent weight. Another observation is that when an object is less dense than a fluid, it floats. Right? For example, the human body floats in water, a helium balloon floats in the air. And so to explain this phenomenon, we use something called Archimedes' principle. And saying it in words on this slide, and then on the next slide we'll talk about it using math. But in words, when a body is completely or partially immersed in a fluid, the fluid exerts an upward force on the body. Okay, so that's the first important concept. This force is always upwards. And the magnitude of that force is equal to the weight of the fluid displaced by the body. So the magnitude of that force has nothing to do with the weight of the actual object. It has to do with the weight of the fluid that the object has displaced. So the object has pushed some fluid out of the way. Right? For the brick in the previous example, there would have been some fluid here, right, in that volume taken up by the brick now. It's the weight of that fluid which is equal to the magnitude of the buoyant force on that brick. Okay, and so again, here's Archimedes' principle in words. And in equation form, the buoyant force, we're going to use the symbol B for that. As Archimedes' principle says, it's equal to the weight of the displaced liquid. Okay. The buoyant force is just equal to the weight of the liquid that would have been where the brick is, but it's not there anymore. It's been displaced, it's been pushed out of the way. So what is the weight of the displaced fluid? Right? That's just the mass of the displaced fluid times acceleration due to gravity, right? Our weight formula. What is the mass of the displaced fluid? Well, we know density is mass over volume, so that means that mass is density times volume. Right, so if I want to know the mass of the displaced fluid, I just have to multiply the density of the fluid times the volume of the fluid that was displaced. Okay, and so the total buoyant force I find by multiplying the density of the liquid multiplied by the volume of the liquid that we've pushed out of the way times g. Right, this is how we're going to calculate the buoyant force. This is Archimedes' principle. And so on the equation sheet, you'll see something like this. The buoyant force is equal to the density of the liquid times g times the volume that was displaced. Okay, so when we, this is just another conceptual picture of this, right? If I have a rock which I've submerged underwater, it's pushed some water out of the way, right? All the water that would have been right here, all of this water has now been pushed out of the way. It is the weight of that fluid, right, that is equal to the buoyant force, right? So the actual mass of this rock doesn't really matter. What matters here is that the volume of this rock pushes away some volume of fluid, displaces that much fluid, and we have to know the density of the fluid. If we know the volume of that fluid, we can calculate the weight of that fluid. Okay, so that's Archimedes' principle. And we can do kind of a back of the envelope kind of derivation of Archimedes' principle just for a box, for a nice simple box, and just to understand it from a different perspective. If I have this box, I've submerged it underwater, well, I know that the pressure at the top of this fluid is equal to atmospheric pressure, and I know that pressure increases with depth, right? This H is the depth measured down from the surface. And this is our formula for pressure at a given depth, right? It's equal to the pressure at the top of the fluid, atmospheric pressure, plus the density of the fluid times G times your depth. All right, so if I want to know the pressure at this location, at point 1, I can use this formula. If I want to know the pressure at this location, point 2, I can use this formula. Right? I know that point 2 is deeper than point 1, so the pressure is going to be bigger at point 2 than it is at point 1. Okay, so the pressure at point 2 is larger. I also know that pressure is equal to force divided by area, which means that force is just pressure times area. So if the pressure at point 2 is larger, and the area of the bottom of the box is larger, I'm sorry, if the area of the bottom of the box is the same here as it is here, but the pressure is larger at the bottom, that means the force on the bottom of the box is larger, which means this force upwards on the box is going to be bigger than the force downwards on the box from pressure. Okay, and you can see we're going to get a net force upwards from pressure, basically. If the pressure on the top of the box is smaller than the pressure at the top on the bottom of the box, and therefore we're going to have a net force upwards, which is going to be this buoyant force. Okay, that's if this box is just floating here, that buoyant force upwards must be exactly canceling the force of gravity downwards. Okay, so we can try to estimate the magnitude of this buoyant force. I'm just going to say buoyant force is equal to F2 minus F1, meaning it's the pressure on the sides of the box is just canceling, but the pressure on the bottom of the box is larger than the pressure on the top of the box. Right? So the net force is going to be F2 minus F1. F2 in the positive direction, F1 in the minus direction. F2 is just pressure times area, same thing as F for 1. I can replace my pressure with our formula for pressure at a given depth. I plug that in, I simplify a little bit to get this equation. I have rho times G times H2 minus H1 times A. And now I recognize that area of the bottom of the box times the height of the box here, basically, which is what H2 minus H1 is, that's just the volume of the box, right? Area times the other dimension is just volume. So I end up with a buoyant force is equal to rho, our density, times G, times the volume of the displaced liquid. Okay, so that's just a quick proof of Archimedes' principle. And just one other quick idea here. There's one other idea that leads to objects floating, which isn't a result of buoyancy, and that is surface tension. Okay, so in addition to buoyancy, there's a separate phenomenon that allows objects to float. Right? And we're going to not really go into the mass of surface tension, but it is really interesting. So surface tension allows a bug to kind of look like it walks on water. Certain types of coins you can actually float in water. This is an aluminum coin or even a paperclip. A paperclip and aluminum coins are both more dense than water, right? They both should sink in water, but they can actually float on the surface due to this surface tension phenomenon. Right? To understand surface tension a little bit, we know that molecules in a liquid experience some cohesion. They are mutually attracted to each other. Right? So if I look at one little molecule inside this glass of water, that molecule is attracted to all of the neighboring molecules. Right? And that leads to a little drop of water beating up, for example. Okay, but the molecules of water on the surface of the fluid don't have any molecules above them, so they have all this attractive force to the molecules to their side and downwards, but there's nothing pulling up on them. Right? So that leads to this surface tension concept. This is really important for other things. For example, this is why we use soap to clean our hands, to clean our dishes. It turns out the effect of soap is to actually decrease the surface tension. Same thing with washing your hands with warm water or washing your clothes with warm water. As I increase the temperature, I decrease the surface tension, and that allows you to get that water to get into smaller spots and clean things better. Okay, so that's it for surface tension and buoyancy.